Hello, everyone. Welcome to the final class. On electromagnetic induction. I'll be taking the part 2 of that class, and I hope that you pay rapt attention. Let's have a deep dive into it right now. So, electromagnetic induction part 2, we'll be starting with moving a conductor within a magnetic field. So please pay rapt attention. I will not be wasting time at all. Induced current can also be produced moving a conductor in a magnetic field. The direction of such current can always be obtained by applying the Fleming's right-hand rule. Which states that if the thumb, the forefinger, and the middle finger held mutually at right angles to one another, with the forefinger pointing in the direction of the magnetic field, the thumb pointing in the direction of the motion, or we can say of the conductor, of the motion of the conductor. Let me put it that way. Of the motion of the conductor. You see, it's almost like a very extensive, rule, but I will explain with a diagram. Then the second finger will point in the direction so we've established the forefinger, the direction of the forefinger, the direction of the thumb. So what we're left with is not second, let's say middle. The middle finger will point in the direction of the induced current. So please take note of that. And I'm going to draw it now. This is the thumb, this is the other finger, and this is the middle finger. So these are the other ones left. So this is a particular hand. Let me establish the connection here well. We'll have 2 fingers left after the thumb. So this is the thumb, and this indicates the motion. So that motion is like this. That is the motion of the conductor. We said that the thumb carries the motion of the conductor. Then the forefinger, this is the motion of magnetic field. Direction of magnetic field. This other guy, which is the middle finger, indicates the motion, the induced current, direction of induced current. So please keep that in mind. That's Fleming's right-hand rule. We now go straight to a subtopic, and that subtopic, AC and DC generators. AC and DC generators. So we start by saying, okay, a machine that converts mechanical energy into electrical energy, or that converts electrical energy into mechanical energy is called a dynamo. When it changes mechanical energy into electrical energy, it is called a generator. But when it changes electrical energy into mechanical energy, it is called a motor. So you see the difference between generator and motor. So there are two classes of generators. And they are the AC, alternating current generator, and the other one is direct current, DC generator. The AC generator consists of an armature, that is a rectangular coil consisting of a large number of tons of insulated wire wound on a laminated soft iron core. It also consists of a magnetic field created by the curved poles of a horse of a horseshoe magnet or an electromagnet. It also consists of two copper slip rings to which the ends of the rectangular coil are connected and which rotate with the armature. It also consists of two stationary carbon brushes, which are made to press lightly against the slip rings. So let me give a sketch of that, how that AC looks like, AC generator. So I see magnet, north, south pole, then magnetic flux flows from north to south, and this is still the line for magnetic flux. And then I have in between, I have the conductor or wire loop. So this is conductor, and the other one is also conductor, wire loop or conductor. And then I now have something here, or better still, I put one first, and then I put another one. So these two things are slip. Then by the side, I put something. So these two things itself, okay. Let me do it this way. This is the ring right here, and that ring here. So this is conductor running through. So I put something here, put something here. I can call these two slip rings. Why this thing that we see here are carbon brushes. So, and the axis of rotation, the way the rotation is happening is like this. So this is the rotation, and a straight line that goes through is the axis of rotation. So this is how the rotation is happening. You can see it. So take note of this diagram. It's a simple sketch of how the AC generator looks like. It's a sketch. So it also reminds you of some of the basic things that are there. Let's go straight to the direct current generator. The direct current generator, DC. So the idea here is that the direct current generator is produced by replacing the two slip rings with a single split ring, or what we call a commutator. So take note of that. So a split ring commutator is split into two segments which are insulated from each other. The ends of the coil are connected, one to each split ring or commutator segment. So please take note of that. A commutator is a current reverser So that's just a short statement. I will now explain that when the armature coil is rotated, the commutator automatically switches each end of the coil from one brush to the other each time the coil completes one half of revolution. When the armature coil is rotated, commutator automatically switches each end of the coil from one brush to the other each time the coil completes one half of revolution. So the idea is that as the current reverses in the coil, so this is kind of explaining how the commutator is the current reverser. As the current reverses in the coil, after each half revolution, the connection between the coil and the brushes are reversed through the action of the commutator. So please take note of that. So that explains how the commutator is responsible for reversing current. So let me quickly give my own sketch of the DC now. DC generator rather. This is not pole of magnet, and that is south pole. And this magnet is not just ordinary magnet, it's permanent magnet. Then we have the conductor. This current flow, this is the way current is flowing. Current is flowing like this. Then we have one single, okay, but one single commutator which is split into two parts, one here, one here. So this is a commutator. There's a carbon brush somewhere here, carbon brush here too. So it's two things, carbon brushes. And they are connected to a galvanometer and then connected to this side. So this guy is a galvanometer. So this place is plus. This particular wire is plus, and this one is minus. So take note of that. Then the axis of rotation is happening like this, and this is the axis of rotation. That dashed line is the axis of rotation. So this is how it looks. So please take note of this simple one. Then this is rectangular coil. Yeah, so please take note of that diagram. You can pause and draw it, but we'll move straight to transformers. What is a transformer? A transformer is an electrical device for changing the size of an AC voltage by increasing or decreasing its EMF. So it's changing the size of an AC voltage by increasing or decreasing its EMF. So just put that in mind. It consists of two separate set of coils. And those two are primary coil, secondary coil. So it's made up of primary coil and secondary coil. The primary coil consists, or let's say is input, is the input winding of turns or wire, and the secondary coil is the output winding of turns of wire. The coils that wound around the soft iron core when you say wound, it's like past tense of wind. Coils that wound around a soft iron core. And the function of the soft iron core acts to increase and concentrate the magnetic flux within the core. And this soft iron core is laminated to reduce loss of energy in form of heat due to eddy current. So please, those are important information. You read them, digest them in your reading jotters. So let me give a sketch of how the transformer looks like. We have some winding here. We have another winding here. These are the primary, coil, secondary, coil, and then we have N2 turns. That's number of turns here. N1 turn. Oh no, not N2. Let's say NS. NS turns. NP turns here. Primary turns. The current flowing here is IP, and the voltage. So this is current, and voltage is VP. Voltage. So in this core, in the transformer core, this transformer core, there is some magnetic flux flowing in that direction. So it is passing through. It's not just flowing, it is passing through the coil. Magnetic flux. So that's it. This is the transformer core. So that's the sketch. So let's quickly now. On the other hand, you have IS here as secondary current and VS as secondary voltage. So let's quickly talk about a step-down transformer. For a step-down transformer, I want to quickly go straight to the point. the secondary voltage is less than primary voltage. Let's put it like that. Okay. Step down transformers. These are transformers which reduce the voltage such that the voltage in the secondary coil is less than that primary coil. Don't forget that we call secondary coil. Secondary coil is like output, then primary coil input. So note that what we call mutual, let me quickly define mutual inductance is the flow of induced current or voltage in a coil due to alternating or varying current in neighborhood coil or neighboring coil rather. Neighboring coil. So mutual inductance is where you make current or voltage to flow in coil B because you are alternating the current in coil A. You see the idea? You alternate the current in coil A, then magically or mysteriously, you have current flowing in coil B. That's called mutual inductance. Take note of that. The idea here is a guiding formula for transformers is that we're going to say EMF in secondary over EMF in primary equal to number of turns in secondary over number of turns in primary. Keep this. That's very important, capital. So E is EMF, and N is number of turns. So take note of that. Then we also have another one, guiding formulas. EMF here to this, the current. This is another one. Take note of this. So the EMF in this case, you see that in the case of current, there is a switch. In the case of number of turns, S, S, P, P. But in the case of current, S, P, P, S. So take note of that stuff that you're saying. So please keep that in mind. So we can write a general formula by saying ES over EP will now be equal to NS over MP, and it's equal to IP over IS. So from there, you can derive this relationship. So keep that in mind. So let's talk about step up now. Step up transformers. Don't worry, all these equations up here, they are transformer equations. So these are transformer equations. So we use, so step up transformer now, quickly, the idea here is just these are transformers used to increase an applied voltage. That is to make ES greater than EP. That is than EP. That is, we are saying in the case of step down, we are saying that the voltage in secondary is less, but now we are saying that the voltage in secondary is higher. So secondary coil voltage is higher than primary coil voltage. As simple as that. So keep that in mind. We'll now talk about energy losses, rather. Energy losses in transformer. So there are 4 of them. Number 1, or let's say energy is lost due to high eddy current. And let me quickly explain that. This reduces the efficiency because they consume power. Because the transformers consume power and energy is lost in form of heat. This loss, that is the one due to eddy current, this loss can be reduced. This is an important OBJ question. Can be reduced by laminating the core. Please take note of that. And let's move forward. There's another one, energy loss due to hysteresis. And this loss, this is wasted energy. Let me put it, this is energy wasted, let me put it, due to reversing the magnetization of the core. When you reverse the magnetization of the core, you cause hysteresis. It is reduced by use of special alloys. In the core of the primary coil. By use of special alloys in the core of primary coil. Then the one where we have heat loss, primary, in this case, the primary and secondary coils have resistance. Some energy is lost in form of heat due to that resistance. That energy is I square R. So this is reduced by using thick wires or low resistance coil. So that's the idea. And the fourth one is that loss due to leakage, energy loss due to leakage of magnetic flux. This arises because not all the lines of induction due to current arises because not all the lines of induction due to current in primary coil pass entirely through the iron core. The loss, it is reduced by efficient core design. So please take note of that. And then let's quickly take some examples, which will now give us the permission to call it a day. Take a couple of examples. We should be fine. So let me also mention before the example that without all of these losses, the ideal transformer should be 100% efficient. Do you know that the idea of a transformer is the conversion of input to output? That is, we have input to output because the primary is input and then we come out through the secondary output. So normally if these losses don't occur, it's supposed to be 100% efficient. That is, nothing is lost. But because of these losses, there is no ideal transformer in reality. That is, we don't have any 100% efficient transformer. So please, let's take examples now. Examples of questions under this. And the first example is find the turns ration, or I think that should be ratio. Or let's say ration. In a transformer, which delivers a voltage of 120 volts in the secondary coil from a primary voltage of 60 volts. So you see that right there. We're looking for turns ration. So now we know that the idea is ES over EP equal to NS over NP. Now ES, the secondary coil, we are given 120. Primary, we are given 60. So that's definitely equal to NS over NP. So clearly, this is the turn ratio. Ration or ratio, any of them. So but this is the idea. So the ratio of the secondary turn to the primary turn is just exemplified in 120 to 60. That is 2:1. 2:1. So let me adjust this thing as ratio. That is ratio, turn ratio is 2:1. So take note of that. The other question, other example, is a transformer has 500 turns. in the primary coil. And 300 turns in the secondary coil. If the primary coil is connected to 220 volt mains, what is the voltage? Or what voltage? What voltage will be obtained in secondary coil? So it's the same idea, the same formula. And then we want to tell what type of transformer is it? So the idea here is that the primary turns we see from the question 500 and the secondary turns 300. We're not told that the voltage VP is 220. Or when we say voltage, we can say EMF as well, can be used. So EP is 220. Are you seeing that? 220 volt. Then ES is what they asked us to find. And let's use the normal formula. ES over EP equal to NS over NP. So we're looking for ES over 220 equal to NS 300 over 500. By the time we do the math, we have 220 times 300 over 500. By the time we do this, we have, let's do 220 divided by 5. I have 4 here, 2 here, no, 44. 44 is 44. So that would now be 44 times 3. That should give me 132 volts. So we see clearly that the ES is 132. And we know that ES is normally output. So what was EP? EP was 220. Now, since this is the input and the output is less, from 220 to 132. That means it's a step down. Because they asked us what type. Step down transformer. Because it is a step down transformer because ES is less than EP. ES is output. So let's look at the last example for today. That is where we talk about a transformer. Example 3. A transformer supplies 15 volt from a 220 mains. If the transformer takes 0.7 ampere from the mains when used to light 3 lamps connected in parallel, and each rated 15 volt, 40 watt. Calculate first the efficiency of the transformer. Yeah, I'll give you a new formula. And then the cost of using it for 24 hours at 30 kilowatt per hour. Let's say 30 kilowatt hour. 30 K per kilowatt hour at 30 K per kilowatt hour. So I will get to understand what that means exactly later. 30 K per kilowatt hour. So let's find the efficiency first. And the idea for efficiency here is output power. Let me give you the formula first. Efficiency, please take note of this formula. Efficiency, when it comes to transformers, is equal to output power over input power times 100%. Let me circle the entire thing. So take note of that. So let's find output power. Output power we have to do with the secondary coil, right? So from a question, we see that it supplies 15. The idea here is that the output is 15 because you are seeing the word supply from 220. This is the primary. So input is 220 and then supply 15. So output power will be now, what are the formulas for power? We know that power, when you have this thing, power is IV, current times voltage. So output power is I secondary times V secondary. I secondary times V secondary. So the I secondary that we see, if the transformer takes 0.7 from the mains, hold on. So let's see how we can find the we already, this 0.7 from the mains is already input power because the mains from the 220 volt, well, what we call mains, is already, this is input voltage, that's primary, and then 0.7 mains is input current. So, but in order to find output current, we'll look at what the electricity was used to power. It was used to power 3 lamps connected in parallel, each rated this. So let's see. We can find I, because we are given those 3 lamps, each of them rated. But let's see. Let's find the power in each of them. But the rating for each of them was, see it right here, 15 volt, 40 watt. So we can use, the power is 40 watt, and the voltage was what? 15 volts. So we can find the current from there because P equal to IV. We say I equal to what? P over V. So we do 40 over 15. So each of them had a current of 2.67. So the total current in them now will be, that is the output current. That will be 3 times 2.6. So you get the idea. So we have 8 ampere. So we'll come back here and say, okay, 8 ampere times the output voltage is 15, like I said. So 15. So the output power is now 120 watt. So, but the input power is direct. From the question, we see that mains, where you see the mains. So that's IV, IP, VP. So that is right here. IP is 0.7 ampere. I see it from the mains. So say 0.7 times VP voltage from 220 voltage mains. That's the mains. 220. When I do that multiplication, I obtain 154 watt. So if I do efficiency now, I put output, which is 120 right here, over input, 120 over 154 times 100%. And I see that this is 78% efficient. The other thing I was asked to calculate is the cost. The cost of using it for 24 hours at 30K per kilowatt hour. So let's see, let's find the total kilowatt hour there first. Total kilowatt hour, I can find out by saying, okay, the power consumed is IV, that's primary, 0.7 times 220. That gives me 154 watt. If I divide that by 1000, I get 0.54, 0.154 kilowatt. So now, okay, we're asked to find the cost of using it. Okay. Oh, if we say the cost of using it, we are referring more to the bulbs this time around. So we cannot be using the power consumed. We focus on the secondary. So that has to do with, let me go back to the, that's 8 times 15. So that was 120 watt. Because this is what entails when we're using the bulb. Yeah, when we're using the bulb, because this is the rating of the bulb. So you see it supplies this from the mains. So this is what we're using. So if we divide that by 1000, we have 0.12 kilowatt. So we want to get it in kilowatt hour. So how many hours are we using for 24 hours? In kilowatt hour, we now do 0.12 times 24. So I can quickly calculate that as, let me grab my calculator. 0.12 times 24. That gives me 2.88 kilowatt hour. Now, they said the charge is 30K per kilowatt hour. That's what the question said. Go back to the question. 30K per kilowatt hour. Just like saying 30 naira. So per kilowatt hour. So whatever K is. So since we have this amount of kilowatt hour, the amount we spend is 30 times 228. So the amount we spend now is 86.4K. So keep that in mind. That's how much you spend for keeping those things on. Oh, and that 30K is 30 kobo. So this 86.4, yeah, we have 86.4 kobo. So That's what we have to spend to keep those things. And if we convert that to Naira, if we divide it by 100, that would be like 0.864 Naira. So keep that in mind. Just get the ideas from this. And yeah, that is it. Let me just mention some more basic things before we close. So keep all these formulas. Power consumed has to do more with the secondary. So yeah. And then keep all of this in mind: efficiency, output power, all of this. So we'll see in our next class. Please keep studying, keep working hard, and see you.